1.8 is linear equations, linear differential equations. Okay, so far we've learned only one analytic technique for finding solution, the exact solution to a differential equation, and that's separation of variables. But the technique is really limited. It only applies to a certain very special kind of differential equation, separable equations. The qualitative and numeric techniques that we've studied can be applied to a much wider class of differential equations. And so it would be nice if we could expand our ability to find analytic solutions, find a formula for the solution. But this is a really tough problem because although the existence theorem guarantees that solutions to most nice differential equations exist, what do I mean by nice? Continuous, yeah, good. There's no guarantee that they're made up of our old friends, the elementary functions, like ln and e to the exponentials and trig. So, in fact, usually they're not. Okay? Usually the solutions are like these crazy integrals or something. So, there is no general approach to solving a differential equation analytically. Differential equations have been being studied for like 300 years. And over that time, mathematicians have developed many solution techniques for different special classes of differential equations. Our course is going to cover a handful of them. So some of the more classic ones that give you some insight into how a differential equation works. Because you don't have to learn every single analytic technique out there anymore because we have these great things like Mathematica and Wolfram Alpha, but it is important that you sort of get a flavor of what those computer programs do. So we're going to develop one of the standard techniques for solving linear differential equations today. So this only applies to a very small class of differential equations, linear. So a linear differential equation, so first order, anybody remember what that means, first order? First derivative, good. And it's linear if you can write it like this. So dy dt is a function of t times y plus another function of t. So in other words, a differential equation is called linear if it's linear in its dependent variable, right? The y is the thing that's linear. The exponent on the y is just a 1. All right, so quickly in your groups, decide which of these are linear and which are nonlinear. Yeah, yep. So a of t and b of t are functions, yeah, of t. So you can have any kind of crazy stuff with t's as long as y is linear. Okay, so this first one, yes, because the a of t is t squared and the b of t is cosine t. So this says a of t times y plus b of t. How about this one over here? No, because the y squared, there's a 2 on the y, which makes it nonlinear. Okay, how about this crazy looking one down here? Yes, okay. My a of t is that guy, and this whole thing is b of t. So I have a of t times a y plus b of t, another function in t. How about this dp dt? Yes, now my dependent variable is now p instead of y, so I need to have an a of t times the dependent variable plus a b of t. Okay, so this one is a little harder to see. What did you think it was? Yes, linear. So it helps if you solve it. So it looks like dy dt equals 3y plus ty plus 2. And then you can factor out a y. So it would be 3 plus t y plus 2. So what's the a of t? Yep, and what's the b of t? 2. Good. Okay, let's do those two last. Dy dt negative 2y plus 8. Yes. Yep, A of t is -2 and B of t is 8. dw dt is the sine of t times w. Yes, my A of t is sine t, and my B of t is 0. Just the function B of t equals 0. How about dz dt equals t sine z? No, because sine of z, that is a nonlinear function in the dependent variable. So the only nonlinears were the first and last in the second column. All right, so linear differential equations come in two flavors. If B of t equals 0, we call that a homogeneous or unforced differential equation, linear differential equation. Otherwise, when B of t is non-zero, we call it a non-homogeneous or a forced differential equation. This is just vocab. So which of these is the homogeneous linear differential equation? The first one. Yep. We've got an A of t, a function on that is sort of the coefficient to y, and B of t is 0. In the second one, my A of t is 1, and my B of t is sine 2t. Okay, so this one is homogeneous. And this one is non-homogeneous. All right, every non-homogeneous linear differential equation, dy dt equals a of ty plus b of t, has an associated homogeneous linear equation, which is just the equation where you drop the b of t. We call that the associated homogeneous equation. So this was our non-homogeneous equation, right? So the associated homogeneous equation would just be dy dt equals y. You just drop the b of t. This is the associated homogeneous equation. Okay, so now we have sort of all of our definitions under our belt. We can dive into how to solve these things. So there's a couple of important principles of linearity. They're going to seem like I pulled them out of nowhere. I will prove that they're true, but we're going to kind of prove it by going backwards, which makes it seem like, how did anybody ever figure this out? But they've been looking at it for 300 years. Of course, someone would figure it out, right? Yeah, I know. So the first principle of linearity is that the non-zero solutions of a homogeneous linear equation, so that's one that has no b of t on it, it's just a of t times y, are all constant multiples of each other. So that is, if you know one solution, throw an arbitrary constant in front, and you have the general solution. So we're going to verify it. I'm going to write down a generic homogeneous linear equation, a of t times y. And then I'm going to suppose I have a solution. I'm going to suppose that y sub h of t is a solution. Just a solution, not the most general, but a solution. And I put the little sub h for to stand for the homogeneous equation. It's going to be a solution to the homogeneous equation. I want to show, NTS need to show that k times this solution is also a solution. Okay, so that's what the principle says. It says that if you have a solution, the other solutions are multiples of it. So we are assuming that we have a solution, y sub h. I need to show that k times y sub h is also a solution. So I have to show that dy dt is equal to a of t times y for for this solution. Okay. So I have to take dy dt. Okay, so we'll call this y. So what is the derivative of k times y sub h of t? Times k, right? The constant, the coefficient comes along. So this is going to be k times y sub h prime of t. And then a of t times y well, a of t is just a function in t, and I don't know what it is. It's arbitrary. So I'm going to have a of t times y, which is k times y sub h of t. So for these two things to be equal, what has to be true? Yes, y sub h prime right here. On the bottom, no, I'm just plugging in a of t times y. So I'm just plugging into the right-hand side. So I'm plugging into the left-hand side, plugging into the right-hand side, and I want to show that they're equal. Yep. But it's the same on both sides. Yes. For these two to be equal, this has to equal those two, right? So y prime, that's dy dt sub h, right? Has to equal a of t times k times y sub h. But k times y sub h, that's y. So this is a of t times y, which is the original equation. I know that this is true from my initial equation. So let's do an example. So the proof is kind of like, there's so much notation in it and stuff. So if we do an example, I think it'll be clearer. So here I have dy dt equals cosine of t times y. So this is a homogeneous linear equation. There's no b of t term. So if I were to, I'm going to give you a solution. So given that y equals e to the sine t is a solution, right? We want to find all solutions. So my principle of linearity says that all I have to do is throw an arbitrary constant in front of this, right? My general solution would be y equals k e to the sine t. And we can verify that that is the general solution by separation of variables. So I would do 1 over y dy equals cosine t dt. Integrate ln of y equals sine t plus c. Raise e to both sides, and you get e to the sine t plus c, which we could do our little trick, e to the sine t times e to the c, but e to the c is just an arbitrary constant, k. So there's our most general solution, which is exactly what the principle of linearity predicted would be the general solution. All right, so that's our first principle of linearity. The second principle of linearity says that the general solution of a non-homogeneous equation is the sum of the general solution of the homogeneous equation, which principle 1 tells us a little bit about how to find, okay? The sum of that guy, and one particular solution of the non-homogeneous equation. Anyone, yeah. So that's what makes this powerful and difficult. So you only need one. You don't need the most general one. You just need any function that will make that differential equation true will serve. And if you add that to the general solution of the associated homogeneous equation, you get the general solution of the non-homogeneous. So you can verify it using the same technique that we used for principle 1. I'm going to let you do it on your own sometime. We're just going to practice using this. All right, so here is a non-homogeneous linear differential equation. So the associated homogeneous equation would be dy dt equals cosine of t times y. Right? And we just solved this like 2 minutes ago, right? We found that the solution there is k e to the sine t. And I'm going to throw a little h on here for the solution to the homogeneous equation. So now I have half of the general solution to my original problem. Okay, my general solution is the sum of that, y sub h, to any particular solution to the whole equation. So I'm going to give it to you for now. I just want you to show that y sub p for particular, okay, equals t over 5 is a solution to the given ODE. Okay, so take a minute to substitute, okay, find dy dt and plug in t over 5 for your y's over here, show that they're equal. Okay, so to verify that a function is a solution, we just substitute. Okay, you don't have to actually try to solve it and get t over 5. You just substitute. It's like back when you were learning how to solve equations, I could say, is x equals 3 a solution to the equation x plus 5 equals 8, right? You just take the 3 and you plug it in, and you go 8 equals 8. Yep, it's a solution, right? So I'm going to do the same thing. I'm just plugging in. So if y equals t over 5, then dy dt is 1/5, right? The derivative of t over 5 is 1/5. And then the right-hand side of this equation, cosine t y plus 1/5, 1 minus t cosine t. Okay, so I'm going to evaluate this, and hopefully I get 1/5. I want the left side to equal the right side. So I'm going to replace the y with a t over 5. And oh, yay, look at that. Cosine t times t over 5 minus t over 5 times cosine t, those are the same. They cancel, and I get 1/5. So 1/5 equals 1/5. The left side equals the right side. And I know that I now have verified that t over 5 is a solution. So I'm gonna write it out one more time. Plus 1/5. And I want to show that y equals t over 5 is a solution. So plug into the left. dy dt is 1/5. Plug into the right. Oops, this isn't t cosine t, it's y cosine t. And then y is t over 5 cosine t. Okay, so all I'm doing is plugging in. I have my y, I plug in dy dt and y. Simplify both sides. These terms cancel, and we get 1/5 equals 1/5. So I know that that y was a solution. So I know that that's a solution. So now that I know that it's a solution, I can write out the general solution to this differential equation. So what I have found is a particular solution, as opposed to the whole family of solutions. So the general solution would be y of t. It's equal to y sub h, right? The solution to the homogeneous equation that we found, the general solution to the homogeneous equation, plus y sub p, the particular solution we found to the whole ODE. So this is going to be, this was k e to the sine t, and my particular solution, which was t over 5. So finding the general solution wasn't difficult, right? We were able to get it by separation of variables. It was the particular solution, I just magically pulled it out of thin air, right? So that's going to be the hard part. But this does lead us to sort of a step-by-step process. If you can find those two things, then you can find the general solution. Yeah, you guess. Mm-hmm. Yep. Time-tested mathematical technique. I'll show you a way to guess well. So the principles of linearity lead us to this 3-step procedure for solving a linear differential equation. 1, find the general solution of the associated homogeneous equation. Find one particular solution of the non-homogeneous equation. And 3, to obtain the general solution to the non-homogeneous equation, add the results from 1 and 2. So the limitation with this method results from having to find a particular solution to the non-homogeneous equation. Okay. The homogeneous equation is not bad because it's also autonomous. It only has y's in it. That's not true, but it's separable. It's separable, so you can solve it by separation of variables. The particular solution is harder. And if a of t isn't a constant, the function in front of the y, if that's a function in t as opposed to just a constant value, it can be really hard. So we're just going to focus on when a of t is constant. So we're narrowing down the applicability of this technique. We're just going to focus on one. A of t is a constant. And when that's true, you can sometimes find a particular solution by guessing. Yeah, we just have to guess. Okay, so here's an example. I want to find a general solution to this non-homogeneous linear equation. So step one, remember, was find a solution, the general solution to the associated homogeneous equation. So I'm going to do dy dt equals negative 2y, and that's what I want to solve. Okay. The a of t, the function in front of the y, is just the constant negative 2, which makes this easily separable. I can solve this by separation of variables. Okay, so I get 1 over y dy equals negative 2 dt. Integrate. Ln y equals negative 2t plus c. Raise e to both sides, and I get y equals k e to the negative 2t. So halfway there, I have the solution to the the associated homogeneous equation. This is half my general solution. Now I have to find a particular solution, just any solution, any function that will make this differential equation true. If I can find one, I can create the whole family by adding it to this guy. So it helps if you write this by moving the 2y to the right. It can help us guess a solution. You move the 2y to the right. So I'm looking for a function who, when I take its derivative and add it to twice itself, e to the t pops out. So I'm looking for a function that when I take its derivative and I add it to 2 times itself, I get e to the t. So what kind of function? So yeah, like e to the t is floating around in my brain because its derivative and it is itself. So I'm thinking, okay, maybe it's e to the t. Let's just guess e to the t. It's just a first guess. Let's check and see if it works. So if I take dy dt would be e to the t plus 2 times y. I actually get 3 e to the t and not e to the t. So e to the t is not the solution, but I was only off by a constant, by a factor. So if I use a 1/3 instead of just plain old e to the t, use 1/3 e to the t, that could work. No, because then you'd be leaving off this whole piece of the general solution. Yeah, but it's not all the solutions. You found a family, but the family is really bigger than that. Yeah. So I'm going to say, well, we're off by a constant, and it's pretty clear that that constant factor is 1/3. But let's say we didn't know what it was because this is more complicated. Okay. So we're going to say, well, we're off by some factor, and we don't know what it is. We're going to guess y is alpha times e to the t, some factor that we need to figure out what it is. So I'm going to plug in alpha e to the t. I'm going to use that as my function and try to figure out what alpha has to be based on what I get. So dy dt, if y is alpha e to the t, what's dy dt? Alpha e to the t. Plus 2y, so 2 alpha e to the t. I need that to equal e to the t. Yep. So 3 alpha e to the t has to equal 1 e to the t. and then we match up the coefficients. So 3 alpha has to equal 1. So alpha is 1/3. This is called the method of undetermined coefficients. So my final general solution so I now have found 1/3 e to the t is my particular. Is going to be y of t is equal to y sub h, solution to the homogeneous, plus y sub p, the particular solution that we found to the original differential equation. So I'm going to have y of t is equal to k e to the negative 2t plus 1/3 e to the t. So in general, this is a good approach, is to move the y term to the same side as the dy dt, and then looking at that and seeing what it has to equal, guess what y will work. Simple stuff, yeah. Functions that we're familiar with, that we know their derivatives well. This is a good thing to do. So the process is called the method of undetermined coefficients. Let's do another one. I already know the solution to the associated homogeneous because it's the same associated homogeneous as the last example. K e to the negative 2t. So that's step 1 taken care of. Step 2, I have to guess a particular solution to this differential equation. So I'm going to add the 2y. It's the cosine of 3t. So I need a function that when I add its derivative to twice itself, I get cosine 3t. Any guesses? Yes, we need a guess first, though. Sine of 3t. Okay, let's try it. So guess 1. Y particular is going to be the sine of 3t. Alpha sine 3t. Right, we don't know the coefficient. Okay, so dy dt. Alpha sine 3t would be 3 alpha sine 3t plus 2 times y, so it would be 2 alpha. Oops, this is cosine. Derivative of sine is cosine. 2 alpha sine 3t. Does that equal cosine 3t? Are there any coefficients we can choose for alpha that would make that equal to cosine 3t? Well, my coefficient on cosine 3t is 3 alpha, right? And I need that to be a 1 because the coefficient on cosine 3t over here. So if I make alpha 1/3, I'll get the right coefficient on cosine 3t. But then I end up with an extra 2/3 sine 3t. There's no alpha I could choose that can make this thing equal to cosine 3t. So this didn't work. Okay. And the problem was that I had an extra sine term. Okay. I don't want to have any sine terms after I add them together. So I need another guess. What about alpha cosine 3t. Will that work? Possibly. Okay, so let's try it. Alpha cosine 3t. Sine didn't work, let's try cosine. So dy dt, the derivative of alpha cosine 3t would be negative 3 alpha sine 3t plus 2y, so this would be plus 2 alpha cosine 3t. Does that equal, can we make it equal cosine 3t with an appropriate choice of alpha? We can't. We have that extra sine term, right? To make the cosine terms match, I'd have to make alpha a 1/2. But then when I make alpha a 1/2 over here, I have this random sine term, so they're not equal. We need some combination of the two of them. Well, I only, yeah, exactly. That would give it, if we choose a combination of the two of them, we can have a different coefficient on the sine and the cosine. Yeah. So guess 3. I will let y particular be alpha, yes, sine 3t plus beta cosine 3t, or alpha 1 and alpha 2. So this way I can have different coefficients on the sine and the cosine term and try to make them cancel out. So remember, this is my differential equation. It's supposed to come out to cosine 3t. Okay, so dy dt would be 3 alpha cosine 3t plus 3 beta, sorry, minus 3 beta sine 3t. So that's my dy dt, just taking the derivative of this. 2 times y, so this would be 2 times alpha sine 3t plus beta cosine 3t. We want that to equal cosine 3t. Can we make it equal? So let's just start by simplifying the left side here. So I've got 3 alpha cosine 3t minus 3 beta sine 3t plus 2 alpha sine 3t plus 2 beta cosine 3t combine your like terms, my cosine 3t's. So I've got 3 alpha plus 2 beta times cosine 3t. And then my sine 3t's, I'm going to have plus 2 alpha minus 3 beta sine 3t. I want that to equal the cosine of 3t. So now I need this coefficient 3 alpha plus 2 beta. What do I have to set that equal to? 1. So the coefficient on my cosine 3t needs to be a 1. What should my coefficient on the sine 3t be? 0, because there's no sine 3t on this side. So to make these things equal, I have to say, well, 3 alpha plus 2 beta needs to equal 1, and 2 alpha minus 3 beta needs to equal 0. And then I solve this system of equations. So I'll do a substitution. So 2 alpha minus 3 plus 9 alpha two plus 4.5 is 6.5. Alpha is 3/13, which means that beta 1 minus 3 alpha. So 3 alpha would be 9/13. 13/13 minus 9/13 is 4/13 over 2. 8/13? 2/13. Thank you. So now I know alpha and beta. So I know that the y particular is alpha sine 3t. So 3/13 sine 3t plus 2/13 cosine 3t. There's my y particular. I managed to guess. Took us a little while. 3 guesses. But we came up with 1. And now when I add this to the y sub h, the solution to the homogeneous one that we found way back, I have the general solution. Okay, so my general solution will be y of t equals y sub h plus y sub p. And then my particular solution, can't remember, 3/13 sine 3t. When you can't separate. Yeah, when you can't do separation of variables. Is that what you're asking?
No, not like that, but like this, like when you use alpha and beta.
So what other method are you referring to?
Just alpha.
Oh, when alpha doesn't work.
But like, I mean, so that's just not the guess right now.
Experience, yeah. So in general, things that have e to the t on the right are going to be some combination of e to the t's, right? And if you have a trig function on the right, like in this case, you're going to use a combination of sines and cosines. So in general, we'll come back to this. In general, your guess for the particular solution is made up of the same type of functions contained in the b of t, and also sometimes the derivatives of those functions that are in b of t. Sometimes you might guess wrong. When this happens, you just have to try again, with making each guess smarter based on why the first guess failed. This is just a slope field and a few particular solutions to the ODE we just solved. And notice that all the solutions, no matter where I start with an initial value, tend towards the same periodic function. They all converge on that same function. We call that periodic function that they're converging to the steady state solution. It's different than an equilibrium solution, because an equilibrium solution is always constant. But this is a steady state solution in that it always follows the same path. Okay, I think I'm going to skip this last one so that you can go on to the practice.